Now I'm going to dive straight in and show you some code. Here we have a Hello World program that writes its greeting to a file rather than to a screen. There are three system calls here: open, write and close. Now we'll be discussing all the file I/O system calls in detail in the next module, but for now what I want you to notice is first of all that the main function is always the entry point for a C program. The open call, which is our very first system call, takes a file name as argument. And then we see a couple of symbolic constants being used here. This one says that the file is being opened for writing only, and this says that the file should be created if it doesn't exist. That is not a typo. There is no E on the end of create. These constants are powers of 2. They're intended to be bitwise ORed together, as we do here. That's quite common. This final value specifies the access permissions that we want to give to the new file. This rather bizarre octal number, 644, corresponds to the set of permissions that I've shown on the slide. This is the kind of knowledge about Linux that I'm assuming, or hoping, that you already have. So, where do these symbolic constants come from? Well, they come from this header file. Let's have a look at error handling. If you're coming from a Java or a .NET background, you'll be used to having methods throw exceptions when things go wrong at runtime. The Linux System Call API does not throw exceptions. Instead, you test the return value from the call. Most commonly, system calls that normally return a positive integer on success return -1 on failure. So we need to test for that. If there is an error, there's a global integer variable called errno that's set to indicate the actual error. For example, the value 13 means permission denied, and the value 2 means no such file or directory. You're not expected to remember or use the actual values, though. There are symbolic constants that define them. The variable errno and the various symbolic constants are defined in the header file errno.h. Now errno is only set if an error has occurred, so we need this two-step approach. Check the return value for the system call, and then, if it's negative, examine the value in errno. The library routine p_error is a useful little convenience routine. It prints out the text that we give it, foo in this case, then a colon, and then a message corresponding to the current value of errno. Basically, it uses errno to index into a table of predefined error messages. Now, because in C an assignment statement also returns a value, that is, the value being assigned, it's common to see the system call and the error test combined into a single line of code, as we see here. This perform, assign and test idiom is extremely common in C code. Note that this extra pair of parentheses is essential. Without them, the code would call open, test that value for being negative, and then assign the Boolean result of that comparison to FD, which is not what we intended at all. Now, traditionally, the Linux system call interface is documented in terms of its C language bindings, and despite its age, C remains the lingua franca of systems programming. It's a statically typed language, so you have to pre-declare all your variables. It's procedural, it's fully compiled, and it results in tight, compact code. But compared to more modern languages like C# or Python or PHP, it looks quite primitive these days. Although our main focus will be on C in this course, I'll also be taking the time to compare and contrast some of our examples with their equivalents in Python. Python is a somewhat higher level language. It's dynamically typed, it has an OO programming model, and it's interpreted, so there's no compilation step. Now, the man pages, short for manual pages, are the traditional way to document the command line tools, the system calls, the library routines, and so on. They're usually installed locally, but there are websites that keep them as well. You might find the web-based versions more accessible because they're hyperlinked and easier to search. The local copies are accessed via the man command. Now, each man page is allocated a section number depending on the kind of thing it's documenting. So the user commands are in section 1, the system calls in section 2, the library routines in section 3, and so on. Most of the time you don't much care what section number something is in, but sometimes you do, because by default man will find a matching page from the lower numbered section. So man chmod is going to get me the manual page for the chmod user command. And that command is essentially just a wrapper around the chmod system call, but if I want to get the man page for that, I need to explicitly specify the section number with man to chmod. Now, the structure of the man pages hasn't changed much in donkey's years. For a system call or library routine, your initial focus will be on this section called synopsis. Here you'll learn about any header files that need to be included, and you'll see a prototype of the function. It's important to be clear that this is a function prototype. It's not an example of a call to the function. You might also see cross-references to related man pages. Look carefully at the data types in the function prototype. Now, int and void star are regular C types, but what about size underscore t and size underscore t? Well, they're type defs. In fact, a lot of the data types you'll see in the system call man pages are type defs. The purpose of these is to improve portability, for example, between 32-bit and 64-bit systems, though some of the more cynical programmers might think their purpose is to just obfuscate the code. In fact, most of these just turn out to be some sort of signed or unsigned integer, and the types we've shown here are on my 64-bit system. There's excellent documentation on Python too at docs.python.org. It has a searchable index, and you can download it in a variety of formats if you want a local copy or even a printed version. Again, it's important to understand that what the Python documentation is showing you is not an example of a call to the function. Now, many of Python's functions are in external modules that need an import statement to tell the interpreter to load them, but this one is a built-in function. You don't need to import anything. Also notice that Python, unlike C, supports function calls with optional arguments. In this example, all the parameters after the first one have a default value assigned and are therefore optional. Now, most of the stuff you'll see in this course, at least the C language stuff, is formally standardized in an IEEE standard known as POSIX 1. It specifies an API for a set of system services. It's careful not to specify what the underlying operating system should be. It is, however, closely modelled on Unix. In fact, there's a subsystem called Subsystem for Unix-based Applications that provides POSIX compliance for Windows. And I did, in fact, consider calling the course POSIX Systems Programming, but decided against it on the basis that most people probably wouldn't know what it meant, and I haven't been fastidious in this course about pointing out subtle differences between the Linux implementation and the various standards. Okay, time for a demonstration. We'll make sure we've got the necessary development tools installed, and we'll write and compile and run Hello World, and I'll pay some attention to error handling.